All right, Year 11, welcome to week 7, isn't it, of term 2 now, and our journey into complex numbers begins right here. Okay, just want to make the point straight up here that complex numbers arise from a need. All right, they came out of a need. They're a human construct, just as any other number has been. Civilization, if you can call it that, was around many centuries before numbers were needed, used. But as we became more sophisticated and numbers got introduced, then we started to look for different types of numbers to solve the sorts of problems that we had. So the initial problems were just about having a way of representing numbers. So the Roman numerals were a classic here of just 1, 1, 2, 1, 2, 3. So just using basic matchstick style representation. And in fact, our current number system, 1, comes out of really joining, looking very much like it's developed from, again, a very matchstick type approach where it was just basic counting, just putting together 1 stick per unit. Okay, so that's it all comes from counting. Now, as problems were introduced, so these are our counting on natural numbers, but we at some point we wanted to represent perhaps, what happens if you add 1 to a number and get 0. We need a new number for this because our numbers here don't account for that. Or what happens if we've got perhaps we've got 8 portions to divide between I don't know, not 2 people, but say 3 people or 5 people. How do we do that? So then the whole number system doesn't work for us here. We're going to need to come up with something different. And again, what happens again? So we've got 8 pieces. We've got 3 people. They're integers, but the combination, the operation that we're trying to conduct, leads to a number that we can't deal with. And that operation there is division. Our operation of dealing with, what's the length of, if I've got 4 here and 6 here, again, I've got a whole number of lengths and I can draw a 4 and a 6 and that's very accurate. But this length here then, well, that's what number is this? How do we deal with this number? I mean, there was a discovery made that okay, well, if I draw squares on each of these, that means that 16 plus 36, this area must equal 52. But what does that say about this side? So another type of number was required to deal with that. And so this was the irrational numbers, or the surds. So they came out of a need. And so what we will do now is we'll just sort of develop where did the imaginary number come from, the complex number. Because we've run this down as far as we can go, but as we've come up against solving quadratic equations, we've occasionally been faced with a negative square root, and we've stopped at that point and said, well, we've dismissed the solutions. Well, that moment forever changes now, because we are going to introduce a new number and perhaps, why are we waiting this long? Because the complex numbers arise from a need to solve equations, and we'll have a look at how that develops now. So it all comes from algebra, and so we can develop this algebraically. So we start by simply saying, okay, using some arithmetic, how do we solve such an equation? Well, our solution here is 1, and the solution to all such problems are the set of natural numbers. Okay, so the N standing for natural numbers. Okay, but then, occasionally we have a situation where we alter our operation to addition, and now, well, we've got -1 as a solution, so we need a new number system to deal with that, and we call that the set of integers. Set of integers, Z standing for Zahl, Z-A-H-L, I think, meaning meaning number, or I think it's number in German. That's the German word for number. So Z is our integer. Solve. So then the situation of the pizza and the people. How do we solve such a thing where we've got perhaps, I'll make that a minus, perhaps we've got one thing to share between two people? Well, now we need to develop a number system that can handle that. And that, of course, was the rational numbers. So now we've got numbers between our whole numbers, and the rational number set of rational numbers is Q. Q standing for quotient, quotient of two numbers. So set of natural numbers, set of integers, set of rational numbers. Okay, so perhaps we just write that. So then, of course, we are struck with the next problem was, well, like the Pythagoras problem up there, the right-angled triangle. What happens when we want to solve this sort of equation? Well, we find, well, there are two solutions, and they're we call them a new introduced type of number, the square root of 2. That's absurd. It's not rational. It's irrational, and so it was dealt that title because it didn't seem a sensible number. It wasn't one that we could write as the quotient of two integers, and so and as you found by your proof by contradiction, it can't be written as a rational number. It can't be written as a quotient of two integers. So it's simply irrational, and this is this tag is stuck with this type of number. So if it's irrational, well, we need a new set of numbers now, and this is the set of real numbers, and this is the largest set of numbers that we have to this point had to deal with or had to entertain. So this is the set of real numbers, encompassing rationals, irrationals, integers, the lot. Okay, so we've built up all of these natural integers, rational numbers. They're all subsets of real numbers, but there's a larger group of numbers that to this point we haven't entertained. We haven't looked at. We haven't taken seriously the solution to this equation. And all we're doing here, if you can just see what we've done, we started with some arithmetic, adding and subtracting. Then we pulled in some multiplication, 2x, and that just made it a little bit more complicated. We had to bring in a set of rational numbers to deal with the solutions. Then we brought in some exponents, and that brought in this need for real numbers. Now, nothing's changed here. The exponent is still x squared, but x squared plus 1 equals 0. So our solution here, and this is where we've arrived, x here is equal to plus or minus the square root of -1. Now, the square root of -1 it doesn't have a real number. There's no number that squares to -1. Nothing on our number line deals with this. And so what was, I don't know, maybe back in this was first looked at and entertained as a notion sometime BC. But it's been more recently taken seriously in the 1500s and 1600s. And it was Leonhard Euler who gave this number the title I for imaginary. And so he said, well, let's call this square root of -1 I, and I standing for imaginary unit. All right, imaginary, I standing for the imaginary unit. Now, I for imaginary is like an imaginary number. Well, it's no more imaginary really than any of these other numbers, except it doesn't fit on our number line. We can't sort of count to it. It's not between any two numbers that we can count to, or we can see, or we can tangibly arrive at. It is a human construct, but so is every other number. So it's so this number I is equal to the square root of -1. That means that we are now going to entertain a solution to such problems as x squared plus 1 equals 0. We're not going to dismiss it. We're not going to dismiss it because we now have a set of complex numbers that we have to work with. Right, so set of complex numbers. Now that completes. There are no more sets of numbers. It's not like in a 6 months' time I'm going to reveal something else. Some other set of numbers is going to pop up. Every algebraic problem, it can be dealt with, and we can find solutions to using the complex or the real or the rationals or the integers or the natural numbers. And in fact, the set of complex numbers is the kind of the daddy set. You know, all real numbers are part of it. All real numbers are a subset of the complex, and all the rational numbers, well, they're a subset of the reals, and the integers are a subset of rationals, and the natural numbers are a subset. So, but every single one of those sets of numbers is a subset of the complex number system. So we arrive at the this I being equal to the square root of -1, and that's our imaginary unit, I standing for imaginary. Imaginary because, well, it was first used to solve cubic equations, because in order to solve a cubic equation, if we know what the quadratic formula is, it's x equals -b plus or minus. Now to solve a quadratic, we have to entertain this notion of a surd, the square root of something. Even if that square root disappears, we still have to use it to solve our quadratics. Now our cubic equation, which would go for as long as the width of this page and is incredibly complicated, it has in it, baked into it, it has a square root of a negative number. It has that in there. So when in the 1600s, few mathematicians working hard on cubic equations, they had to entertain this notion of a negative square root in order to solve cubics that didn't have had purely real solutions, but there were negatives in the square roots baked into the working out. Baked into the solution of that cubic. So in order to be able to resolve that, they had to entertain this idea that there was a negative square root. Now, even though that disappeared later on and the solution had no imaginary numbers in it, it was there. And so it was given this title of, this is sort of an imaginary number, and we're just going to handle it. We're going to deal with it because we know it'll disappear. And so it was given that kind of this imaginary or fake or false number. Had a few titles. Fictitious number, I think, was one of them at one point, but it settled on imaginary, and that's the reason why. The history of mathematics is absolutely fascinating. I hope you agree. Okay, so here we are at I equals -1. So let's have a look at how we now use. We've got this new field of numbers to work with, and so we're going to start by having a look at some complex. I've just written there, haven't I? Let's go with complex. I didn't think that looked right. Complex. Let's look at some complex arithmetic to kick things off here. Now, okay. Now, complex numbers are represented by the letter Z. Okay, so for when we're solving algebraic equations, where X is our go-to. Complex numbers are represented by the letter Z. Okay, and it's I strongly suggest we use this little dash here so we don't confuse it with the number 2. So Z is equal to, and this is the representation of a complex number. Z equals A plus IB. Now A and B are real numbers. All right, they are real coefficients. All right, so let's just outline that. Now, this A bit here, this A bit of the complex number is this guy here, is that's the real part of the complex number. So real part of Z, and so we write it REZ to denote real part of z. That's a. That's the a value. Remember, a is a real number. The b part of this number, that is the imaginary part of our complex number, imaginary z. So we write imz, imz. So that's b. That's the imaginary part. Now, if let's say if my real part of z, is equal to 0, then z, what we say is that z is purely imaginary. Right? There's no real part to it at all. And similarly, if my imaginary part of z is equal to 0, then we say that z is purely real. So in this way, we can see that every real number can be written in this format. It just has b equal to 0. So there's no imaginary bit to it. You just have z equals a. So a complex number, z equals a plus ib. That's just our format. That's just how it looks. Let's look at some complex numbers now and putting them together, pulling out, just navigating our way around a complex number. We'll do an example. Okay, so here's some examples for us to look at, just to get a little feel now for how these imaginary numbers work. So, all right, so the first imaginary number we're looking at is this one here, 2 plus 3i. So z, so in a, z is equal to 2 plus 3i. Okay, so the imaginary, so what we're asked to do is state the real part and the imaginary part. Okay, so therefore, the real part of z, is equal to the 2. All right, there's my real part of z, and my imaginary part of z, is equal to 3. And that's it. Real part of z is 2, and the imaginary part of z is 3. In the next video, we're going to look at how this is represented on the complex plane, which looks a lot like your xy plane, except the y-axis is the imaginary component and the x-axis is the real component. So we plot complex numbers on what's called the Argand diagram, a complex plane, and we'll come to that in the next. So now I've come this far, we would plot it, a real part of z, that's my real axis here, real z. My imaginary z is my vertical axis, and so I'd go 1, 2 across, 1, 2, 3 up, and that would be my z there. Z equals 2 plus 3i. That's my point. This here is called either the complex plane, or the Argand diagram. Okay, I'll just leave that there for your consideration, but we'll look more closely at the Argand diagram in the next video. So let's look at the second example, and if you can pause the video and do parts B, C, and D, and come back and check your answers, that'd be excellent. So I think we need to write this out correctly. Z equals 2i minus 5. I'd like you to get in the habit of doing that. And I'd also like you to get in the habit of writing real Z equals, right, so in this case, we've changed the order. I was about to write 2 there. The real part of Z is negative 5, and the imaginary part of Z is 2. So you can imagine it on the Argand diagram would be over into the second quadrant over there somewhere. This, if you like, is not terribly dissimilar to when we represent an irrational number in such a way where we've got the rational component and the irrational component, and we don't put them together. We keep them separate. So this is not dissimilar to that in that way. All right, so part C, Z equals, what have we got here? We've got 2/3 minus root 7i. No problem here. Remember that A and B just come from our set of real numbers. Our real part of Z, real component of Z is the 2/3. And our imaginary part of Z is equal to negative root 7. Fabulous. Okay, and finally D, I'll just do D here. D is, and we often see our I'm going to write this z equals again. Z equals. We often see sorry, I'm finding it hard to talk and write at the same time. We often see a complex number written in this way, where it's just a single fraction. What we need to do is split it up. So this, I want to see quite clearly my real part and my imaginary part. So therefore, my real part of z is equal to root 11 over 4, and my imaginary part of z, well, that's equal to just pi over 4. Okay, I would like you guys to do exercise 3F, and I just want you to do question 1, and then there's a second video which I'll ask you to watch before taking on question 2, and then a third video before we get into question 3. So I'm just giving, I think it's important just to break this up nice and tightly, I think, just as we start out on our complex number journey, because it's a very new area, and I think it's very important that we just don't go rushing into it too quickly. We really understand and feel our way around a complex number, navigate it, get some comfort with it before we sort of launch too heavily. So I am going to we're going to have 3 videos for each of questions 1, 2, and 3. So please watch them, do the examples, and then go and do some practice. So just question 1 for now, and then refer to the second video for question 2.